I work on transaction processing at Facebook. My focus is storage efficiency because we have a lot of data. The key problem for us to solve is to be efficient with storage. I am a software developer. I used to spend too much time in production, not so much anymore. Spending time in production was a great education. So for anyone working on database internals, I've been doing web scale databases, mostly MySQL with some MongoDB and RocksDB for 11 years between Google and now Facebook. Before that, I spent about 10 years between Informix and Oracle and never got near production. And really, once I got near production, I realized how much I was missing. So I encourage anyone who's thinking about a database internals career to spend some time on production. Here I'm going to speak about the relationship between the trade-offs between performance and efficiency, mostly with storage, in the context of RocksDB and InnoDB. So I'll talk a bit. I might be doing a little bit of marketing for some of these projects. RocksDB is an embedded key value storage engine. It was forked from LevelDB many years ago. Since then, it's diverged significantly. The focus with RocksDB is server quality workloads. The focus with LevelDB has been really to favor more maintainable code, simpler code base. So we have a more complex code as we are pursuing more performance. MyRocks is a RocksDB storage engine for MySQL. We've been working on this for several years. The storage engine API in MySQL is extremely difficult to implement. Many projects have attempted to build a new engine for MySQL and failed. We are running in production in one data center on more than 5% of the tier, which is a lot of machines already. So it's in production for the user database tier, which is data we don't corrupt and data we don't lose. So at this point, that's a strong statement. It's going to replace InnoDB, so we'll continue to use MySQL. I'm excited. I want other people to be able to use MyRocks, so it's going to show up in Percona Server and MariaDB Server, which are proper distributions with expert support, so other people can use it. MongoRocks is a RocksDB storage engine for MongoDB. The engine API in MongoDB is much easier to implement. This went from idea to running in production in less than 1 year, and it is in Percona Server today. So RocksDB, when it first got started, there was a lot of focus on performance, but once we began considering using it for MySQL, really it changed to the focus on efficient performance or even just efficiency. The user database tier is tens of petabytes at Facebook. So that's a lot of storage. That's with compressed InnoDB. So we've already compressed it by a factor of 2. The goal is to compress this by another factor of 2. And we are reasonably certain that we can do that from all of the evaluation we've done so far. This pursuit for efficiency, not just the amount of storage we have, but for transaction processing, it's very hard to find anyone willing to use disk arrays today. If you give them a choice, they will choose SSD. So with RocksDB, we are pursuing good read efficiency, better write efficiency, and then best space efficiency. So best space efficiency means we use less space. When you're using SSD, using less SSD is a very big deal. Better write efficiency means write endurance for the SSD is much less of an issue with MyRocks than it would be with InnoDB. The log structured merge tree algorithm that RocksDB uses was invented for disk arrays. The idea was that using less I/O capacity for writes saves more I/O capacity for reads. That's not the selling point for an LSM with SSD. It still turns out to be a great fit for NAND flash because the write efficiency means endurance is less of an issue, and the space efficiency means you're going to use less. So we got lucky. The algorithm turned out to be a good fit for SSD. One of the things I do is I blog a lot, and one of the things I blog about is benchmarketing. And by benchmarketing, I mean the use of unexplained performance results to claim that one database product is better than another. It happens a lot. I do it a little bit, and really the key is the results have to be taken out of context, show a graph, show a few pictures, and so sometimes I don't, in response to this, sometimes I don't even publish graphs. I want people to slow down when they read what I write because I don't want to fall into that. Here, sysbench, it's a silly synthetic benchmark. It has some use. It's widely used in the MySQL community. This benchmark has about 2 gigabytes of data, so it's a very small workload. I didn't run it until a few months ago, and I was happy to see that MyRocks in blue is actually competitive with InnoDB and MySQL 5.6. So I was surprised, and this is the number of threads going from 1 to 128. So even with concurrency, MyRocks held up, but I don't want to explain too much because I'm just marketing here. The problem I see is that we get stuck in this rut about something is faster, so it's better. Really throughput, average throughput or peak throughput is used to rank database systems when we really care about throughput, quality of service, and efficiency. And efficiency, by that I mean how much hardware is used per query or per transaction. And so something that I'm trying to practice, and I hope other people begin doing this as well, is stop doing these graphs and start, at least to complement the graphs, publishing throughput. The first column here, this is TPCC MySQL. 1,000 warehouses, the database is larger than RAM. I had about 50 gigabytes of RAM on the server. So the workload is somewhat I/O bound. Throughput, the TPMC, MyRocks is a little bit ahead of InnoDB. I don't think that's 5% more throughput, I don't think is a big deal. The really big deal is if we look at the hardware efficiency metrics. So here I use IOstat and VMstat. The RKBT is kilobytes read per transaction. And InnoDB is doing a little bit more, but they're not that different. The next column, WKBT, kilobytes written per transaction. InnoDB is writing significantly more data back to storage per transaction. It's less efficient. CPU is a little bit worse for MyRocks, the CPU time divided by the throughput. It's a little bit higher from MyRocks. That's somewhat expected with an LSM. The other really big deal is the database size at the end of the test. InnoDB was almost 3 times larger. So the write efficiency, InnoDB is almost 3 times worse, more than 3 times worse. Space efficiency, InnoDB is almost 3 times worse. And so these are the metrics I care about in addition to throughput. Continuing with my rant, just performance or peak performance is overrated. I think a lot of us, what we do in production is we target good enough performance. We are not trying to run our databases at peak. And we are not necessarily seeking the solution that gives us peak throughput. We have response time goals. And going, let's say, from a 100 microsecond response time to 10 microsecond response time might have no benefit to the business. So once we hit the performance goals, then we want to optimize for efficiency. So can we use less hardware to serve this workload? Or can we continue to use the hardware that we installed this year for another few years as the user demand is growing? From this focus on efficiency, we had one team in pursuit of additional database compression, or 2 teams. One team was working on InnoDB. We got compressed InnoDB deployed in production. We did a lot of engineering work to make InnoDB compression performant for read-write workloads. That code was contributed back upstream. We thought it wasn't clear that we could have additional improvements on InnoDB, so we were looking at alternative engines. We had a team that began working on RocksDB. We wanted these teams to not get stuck on faster equals better, and we wanted these two teams to be able to discuss with each other the differences of, yes, I got better performance, but at this cost of it, worse or better efficiency. So we wanted to make sure the teams were having the full discussion about performance, efficiency, and quality of service. Out of that came what was described as the RUM Conjecture in a paper that was published earlier this year. I am last author on this paper. Came out of researchers from Harvard. The point is that one algorithm or one storage engine cannot be optimal for all of read, write, and space amplification. And I'll go into more details on the slides that follow. Sometimes I use efficiency and amplification as synonyms for each other when talking about this. The paper used RUM, R-U-M, for read, update, and memory. Internally, I've been using, for a longer time, RWS, read, write, and space. So for the rest of the talk, I will use RWNS, but if you look at the paper, it's using RUM. So by optimal, this is an area, a topic, I think, that calls for more research and more formalism. I'm not in academia, I'm dealing with production, so I occasionally try to be formal, but not really. Optimal here is for any useful database algorithm. There's another database algorithm that's better at read, write, or space efficiency, or amplification. And I limit myself to the useful database algorithms. I don't care about we can invent a brain-dead algorithm that is worse at everything. By amplification, I'm usually talking about a ratio. So for read and write amplification, it's the ratio of physical work, either to storage or CPU, per logical request. And I'll define in another slide what I mean by logical request. But it's really a ratio. And we use the term amplification because one algorithm compared to another might actually do more physical work per logical request. Space amplification, the ratio is the size of the database files over the size of the data. Now the challenge with this is it can be tricky to compute the size of the data in the database. You might have to do a select over all the rows and add up the column sizes that you see from the return data. You also might want to include secondary indexes as logical data that you put in your database. So this can actually be difficult to compute for running systems. Work. So I said amplification was physical work per logical request. The work depends on whether we're talking about storage or CPU. So for storage, how many random operations? This is much more of a problem for disk than for SSD. How many disk reads or seeks per second or per query am I doing? How many bytes are being read from storage? How many bytes are being written to storage? For CPU, we can have the notion of work at a higher level. How many pages am I compressing or decompressing? How many memory or cache operations am I doing? If I have a hash structure, how many searches of the hash table am I doing per query? If I have a tree structure, how many key comparisons am I doing? The challenge with these higher level metrics is that it can be difficult to extract them from the database engine and associate them with the individual query. So the one that I end up using most of the time is just CPU utilization or CPU seconds. How much time is spent per query on the CPU? So amplification is work per operation. What do I mean by operation? It would be great if everything could be defined in terms of basic operations: point read, range read, put and delete. And actually, the basic operations here are the API that RocksDB provides. I think of this as a universal database API. Someone could rip out the implementation we have for RocksDB in theory, re-implement that for something other than a log structured merge tree, and they could plug that in with MyRocks and have a faster way of building a new MySQL storage engine. The challenge with using basic operations is they're hard to count. Like for the workloads I run, I usually get from the benchmark utility number of statements per second and number of transactions per second. So it's more common for me to use complex operations when measuring, when talking about amplification. So how do I do this in practice? Well, in practice, knowing that MyRocks does one disk read per query in isolation is kind of boring. I can't use that information. Well, if I'm doing long-term performance regression testing, I can use it. In practice, what I'm doing is comparing MyRocks to InnoDB. With MongoDB, I compare WireTiger and MongoRocks. And so I just look what ratios are interesting. And the ratios are interesting when they're far from 1. And really it's, in 2 cases here, the kilobytes written per transaction, the ratio is 3.71, meaning InnoDB is doing writing 4 times as much to storage per transaction. And then the ratio for database sizes. InnoDB is almost 3 times larger than MyRocks. So what I've done is I've used complex operations, transactions per second or transactions per minute, for the notion of logical request. For hardware utilization, I just use what I can get from IOstat and VMstat. And I divide one rate by another rate to get physical work per logical request. So stepping back, trying to talk at a higher level about a B tree and a log structured merge tree and read-write and space efficiency, using InnoDB as my example for a B tree for talking about read efficiency. If I have n rows in the database, I would do about log n key comparisons on a search. For write efficiency or write amplification, the worst case happens when the page that gets written back to storage only has 1 modified row. In that case, the write amplification is the size of the page over the size of the row. If I have a 16 kilobyte page and a 256 byte row, that's now a factor of 64, the write amplification. If I'm using the InnoDB double write buffer to get torn page protection, so in case there's a partial page write on a system crash, if I want to protect against that, that doubles the write amplification. So the key here is that with a B tree, we are transferring pages back to storage, and the page might be mostly clean when we're writing it back, which is a source of amplification. Space amplification, a B tree subject to random updates, will become about 2/3, the leaf nodes will become about 2/3 full over time, or between 1/2 and 2/3. So assuming the leaf pages are 2/3 full, the database space amplification is 1.5x, meaning it's using 1.5x more space than optimal were you to fully defragment it. So just at a high level, how I think about the B tree, these are the things I keep in mind, whether it's an update in place B tree like InnoDB, for WireTiger, which is one variation of a copy on write B tree, or LMDB, this description actually has to get modified, but I don't have time to go into that. So for a leveled LSM, so by leveled LSM, I mean leveled compaction, which you get with RocksDB and Cassandra. The read, you can think of there as being, there's a sequence of trees, and each, by default, will be 1/10 smaller than the previous tree. So the read cost would be log n for the largest tree, log n over 10 for the next larger tree, log n over 100, log n over 1,000. The hand-wavy answer is you're going to, worst case, do about twice the number of key comparisons for an LSM search than you would with a B tree. Now, the Bloom filter makes it more difficult to figure out what's actually going to happen in practice, but this is the cause of using more CPU with RocksDB. Write efficiency. So the B tree writes pages back, LSM writes rows. However, it doesn't write them once, they're going to get written multiple times. There is a significant benefit generally with an LSM and write amplification, but really the key thing I keep in mind is in one case I'm writing pages, in the other case I'm writing rows. Write amplification for leveled compaction is worse than size-tiered compaction, which is on the next slide. Space amplification, you can't beat what leveled compaction provides. Assuming each level is 10% larger than the level above it, about 90% of the data is in the max level of the tree. If you have an update-only workload, so the database is not growing, you could assume that all of the data above the max level is redundant or garbage. So about 90% is live data and 10% is garbage. Space amplification is about 1.1x. Definitely better than what we'd get from a B tree. Size-tiered LSM, we have this with RocksDB. We don't use it much. Cassandra and HBase offer this. Read amplification is more than a leveled LSM. It's a little bit harder to predict. I think it's going to be highly dependent on the configuration. Again, you can benefit from a Bloom filter for point reads. Write amplification, still rewriting previously written rows, or writing once and then rewriting. It tends to be less than leveled LSM and definitely much better than a B tree. Space amplification is harder to reason about. I'm just going to say it's more than what we see with leveled LSM. For my workload, I care about space efficiency, so I want leveled compaction rather than size-tiered. The summary is interesting. Depending on which one you want, read, write, or space efficiency, which is most important to you, you have a different choice. If you want read efficiency, you're probably going to choose a B tree, at least based on what I predicted. If you want space efficiency, you would choose leveled compaction with an LSM, and if you want write efficiency, you would choose size-tiered. The challenge here is that this frequently is a per server choice. You might have many indexes in your database workload, and the indexes might each require a different choice, and that's just not supported today. I think we are moving towards enabling multiple behaviors in the future. So I did a lot of hand waving. The problem is the hand waving doesn't always match what I measure in production, and I spend a lot of time measuring and explaining performance. It's very painful or expensive. It takes a lot of time, but what I say is usually backed up by measurement. The challenge here is that when you talk about complexity theory or you try to model what I/O performance you will see, the impact of the cache is extremely hard to predict. That with a B tree, we want to have the index in cache, and with the LSM, with leveled compaction, we want to have everything above the max level in cache. If you satisfy those constraints, you can understand the worst case. The other challenge is access distribution. The LSM benefits greatly from skewed distributions. Most production workloads have skew. With an LSM, if you have a small write working set, compaction doesn't necessarily move all the way down the tree. Here is one example. Linkbench is a benchmark based on the production database workload at Facebook. A graduate student for the summer. It turned into like a 6-month-long project for him. Implemented, did the measurements, published the paper in Sigmod, implemented the benchmark. Here I'm providing throughput, efficiency, quality of service metrics. TPS is transactions per second. Comparing MyRocks with compression versus InnoDB with and without compression. So here for throughput, MyRocks wins. For reads per transaction, storage reads per transaction, they're all similar. The big difference is kilobytes written to storage per transaction. InnoDB is almost 15 to 20 times worse than MyRocks. That's really hard to believe. And that was from IOStat. If you look at the Flash device and include the extra writes from Flash grooming or garbage collection, the ratio actually increased to like 20 or 25. And again, it's really hard to believe that InnoDB is doing that many more writes. It's hard to understand. CPU was about the same for all three. Database size, MyRocks was almost 2x, about 2x better than compression for InnoDB, and almost 4x better than uncompressed InnoDB. And the last, the most popular update transaction, response time in milliseconds at the 99th percentile, MyRocks was better. So the next question is, why did this happen? For space efficiency, one problem for the B tree is fragmentation. There's wasted space for pages on disk over time. Another problem, if I don't know who's familiar with compressed InnoDB, is it has a fixed page size. So if we compress a 16 kilobyte page down to 5 kilobytes, and we're still using 8 kilobyte pages on disk. So that compressing down to 5K doesn't do us any better than compressing down to 8K. InnoDB has 13 bytes of metadata that cannot be compressed per row, a rollback pointer and a transaction ID. And then InnoDB doesn't do prefix encoding for keys. RocksDB does prefix encoding. RocksDB only writes out the compressed output, so there's no fixed page size. There's a target page size before compression, and then we compress and just write out the number of bytes that compression output gave us. So for write efficiency, the database is larger with InnoDB, there's more to write. There's another important thing here. We run databases so that the working set doesn't fit in RAM. If the working set fits in RAM and you have fast storage, you're spending too much money on RAM. If you have fast storage, you should make the database use it. So with InnoDB, potentially pages or dirty pages are written back earlier than they would if the working set fit in cache. And so they have fewer dirty rows per page. And again, page over row size is the worst case for write amplification. And then finally, the double write buffer. So InnoDB writes every dirty page twice. One experiment I did was to look at the impact of page size on write amplification for InnoDB. The default at the bottom is 16K, and that's where InnoDB compares worst in the number of kilobytes written to storage per transaction. 19.7 versus 1.25 for MyRocks. When I reduced InnoDB page size to 8K, almost cut the write overhead in half. And then to 4K, there was an additional reduction. So this is at least one of my speculations on why InnoDB is much less write efficient. It's a function of the page size. The problem is I can't use 4K pages in production. InnoDB needs, rows need to fit in half, minus lob columns, rows have to fit in half a page. So if the page is 4K, the max row size is 2K, and that's too small for me. Read efficiency. So I said before that if you look at an LSM, the file structures, you're going to say that, oh, it's going to be less efficient than a B tree. Well, the problem is there's a lot more going on with performance, and in some of my measurements, it's not always the case that the B tree beats the LSM. The B tree advantage is fewer key comparisons and potentially less I/O for range queries. The LSM advantage, at least with MyRocks and RocksDB, is we have prefix key encoding, so we fit more data in cache, because even for uncompressed pages, the prefix key encoding is still done. We don't have page fragmentation. So with a B tree, in the buffer cache, you potentially have pages that are 2/3 to 1/2 full, meaning you're wasting between 1/3 and 1/2 of the memory in your buffer pool because of B tree fragmentation. We don't suffer from that with MyRocks. Another point is that being more efficient on writes saves more I/O capacity for reads, which was actually the initial argument for the LSM with disk arrays. Secondary index maintenance is read-free. With the B tree, it's read, modify, write. You have to read the leaf page, modify it, put it in the buffer pool. Eventually, it gets written back. With RocksDB and MyRocks, We don't have to read the old version of the index pages. And then finally, we have a Bloom filter. Just one experiment I did, I ran the same workload for MyRocks on a disk array that could do 1,000 or 2,000 IOPS, slow SSD that could do about 10,000 IOPS, and then fast SSD that could do more than 100,000 IOPS. And I ran it for MyRocks and InnoDB. The servers all had the same amount of memory, similar CPUs. The interesting thing is the performance ratio between MyRocks and InnoDB. The ratio gets better, favors MyRocks as you move from faster storage to slower storage. So as storage becomes more of a bottleneck, the more storage efficient solution, it looks better in comparison. So my whole point is that we are trading between read, write, and space efficiency, and depending on the different choices we make, either between algorithms or even when we're configuring a database. The first is indexes. Indexes gives you read efficiency at the cost of write efficiency, meaning index maintenance, and space efficiency. You have to store the index on disk. Compression makes reads less efficient in some ways, because if you're reading from storage, you have decompression latency. It improves space efficiency. The trade-off, a common trade-off between write and space efficiency is when you format a file system for a storage device. How much over-provisioning do you do? And if you use half of the storage device, so your percent full is 50, space amplification would be 2. You're using twice as much space as needed because of the over-provisioning. But if you think about worst case cost of garbage collection with the firmware that's reclaiming space to make it on the SSD device, the write amplification, the next formula, would be 2. So we are already to the right on the graph. If we want to minimize write amplification, we're wasting space. If we end up using, let's say, about 90% of the storage device, then worst case write amplification is going to increase to about 10. So just setting up, formatting a file system on an SSD, you have a choice, and the vendor is making a choice for you in some cases, between write and space amplification. So what comes next? I think we have, well, for one, I'd like to see a product that gave me a B tree and an LSM in one instance. In theory, WireTiger can do this. They have an LSM, they have a B tree. They just have not enabled that. It's not clear to me that we're going to build a B tree as part of RocksDB. But I'd like the best of both worlds. The other thing is tuning RocksDB is extremely difficult. It requires a lot of expertise. So I'd like to move to the model where we have the DBA setting high-level goals for read, write, and space efficiency, and then putting the smarts in the algorithm to tune itself in pursuit of those goals. So adaptive algorithms is something that I hope we see in the context of RocksDB and other database engines. The final thing is more open source. So MyRocks is coming to MariaDB server and Procona server. It's available today, but it's in the Facebook MySQL branch. And that's nothing I would suggest anyone try to use except for an evaluation. MongoRocks is in Procona server, so if you want to use that, it's there. We have a lot more innovation coming to RocksDB. Hopefully we'll have, we have optimizations that we think will work well for tiered storage, for example. If you have 3D crosspoint and NAND flash device combined, but we're really waiting for these devices to show up that we can evaluate them. So I blog a lot. My blog's on the right-hand side, small datum. I am a small data engineer in contrast to the more popular big data. I tweet a bit. I market the work of my team. RocksDB has a pretty nice landing page now, and the landing page for MyRocks is not very good yet, but really the goal is to get people to use Procona server and MariaDB server if they want MyRocks. So we have active mailing lists. We have some early adopters who are, most of them are kind enough to work with us because it's not easy to adopt MyRocks at this point. Thank you, and I'm happy to hear questions.
Questions? How does the performance compare? Have you compared it with the WireTiger LSM?
We sponsored the LSM a long time ago before they were acquired.
Right.
So it's funny because we sponsored it when we were working on RocksDB. They don't suggest using it with MongoDB today because they're busy. I talk to Keith and Michael a lot. They're busy fixing performance bugs in the B tree. So it's just their LSM, it's size tiered. So we favor leveled compaction, which would be a problem for me. I just think they need a few more years before they can focus on it.
All right.
With your write throughput numbers or I/O throughput numbers, does that include the writes to the redo log or write ahead log?
Yes, it includes most of my tests now have replication enabled, the replication logs enabled. So I include the redo log for the database and the replication log, except I almost always run with fsync on commit disabled. Fsync on commit is another source of write amplification, so I'm not counting that. So I get some benefit.
Cool. Could you explain in a bit more detail the difference between size-tiered and leveled compaction?
Yeah, so, and I debated I didn't want, in the past I've tried to describe leveled like in my slides and I left them out on purpose. Although then the challenge is if you don't have experience, if the audience hasn't used it. So, well, size tiered is what HBase does. And so you have an in-memory table, and when that gets full, you create a new file. And think of there being a list of files. New files are arriving at one end of the list from when the mem table is full. And then something looks down at this list and picks adjacent files from the list, 2 or more, and merges them and replaces the files it consumed with a larger file that contains mostly the same data. It can drop some data when it's doing the merge. So you just have this list that's slowly getting new files and then being shrunk into a smaller number of files. But it's if you have an update-only workload, you have this huge file at the end of the list, which has all of your data. And eventually, that huge file has to be combined with most or all of the other files. And it's called major compaction. And so the problem with this is when you're doing that, temporarily, you're doubling the amount of disk space you use. So you're essentially creating a copy of that huge file. So if you have a terabyte-sized database, you're going to have a terabyte-sized file. And when that file eventually is compacted, might happen once a day, temporarily you're going to have 2 terabyte-sized files. So this doubling in size and the fact that compaction tends to be, you generally don't have multiple threads consuming one file for compaction, so how long does it take one thread to process 1 terabyte of file is a problem. Leveled compaction, there's more structure. There's the notion of levels. So memtable puts files into level 0. Every file in level 0 is a sorted run. But each file in level 0 can overlap with every other file in level 0. You move down to level 1, and then level 2 and level 3, these levels grow by a factor of 10. So if you have a terabyte-sized database at the max level, you'd have 100 megabytes above it, 100 gigabytes, and then 10 gigabytes, and then a gigabyte. So you'd have this reduction in size like a pyramid. Each level is a sorted run, but physically range partitioned into many files. So the terabyte level at the bottom might be split into 1,000 files. And so then compaction doesn't have to process the entire level at a single point in time. It can do it incrementally. And this is done by, maybe done first by LevelDB. So level compaction has this more incremental compaction process that doesn't temporarily double the size of the database, which we like. It tends to bound the number of levels you will use, and so it gives you a more predictable worst case read penalty and size tiered, but it tends to do more writes to move data from the top of the tree down to the bottom than size tiered, so it's going to cost you in write amplification.
Any final question?
Well, it's not a question, it's just a comment or a proposition. This read-write space trading sounded to me pretty much like the CAP in the CAP theorem. You could well enunciate a theorem with this.
We had a paper rejected initially. They said the RUM paper took like 2 years to get published. And one of the rejections from one of the reviewers was, oh, this is like CAP, but you didn't prove it. Reject. We were sad when it had happened. But I think there is more algorithmic work, academic research to be done to introduce more formality to explain why this is true. For me, it's true in practice, but that could just be an implementation artifact from different algorithms. So I hope it's an interesting problem for academics to pursue. We have the Harvard researchers who did the paper are continuing to work in this space, and they've done a few other papers, but no attempt at formally proving the RUM conjecture.
Okay. Yeah, we can do one more. Yeah.
Okay, so I had when you're comparing InnoDB and actually any tree, I guess, and any NSM, I'll kind of expect the term sequential access to kind of come up, simply because my understanding of LSM is it favors sequential writes. Is that more because we're talking about a copy on write B tree? Or is it more that your experience is that it doesn't matter so much, it being a sequential rather than a workload which sort of randomly addresses?
Okay. So a trigger claim for me in the past has been LSM does sequential I/O, and logically it has n streams of sequential I/O is the problem. So a busy LSM with leveled compaction, you might have 8 threads all doing compaction concurrently. Each thread has a stream of writes it's generating. But there's 8 concurrent. So if you're the storage device looking up, you see interleaving of the writes that are being done, potentially from these streams, depending on the file system and whether it does extend allocation and whether, but what you're going to see is from the storage device looking up, you're going to see if there's 8 sequential streams, unless they're collaborating to only have one pending write at a time, there's going to be interleaving. So if you are a disk, the disk head is still going to be moving more than you want it to. So even unless you have one compaction thread, only doing one compaction stream at a time, there's still concurrent I/O on the right side. But in addition to that, let's say you have 100 concurrent users running. They're going to be generating read requests. So if, let's say you have one disk head and even only one compaction thread doing this sequential write, concurrent with that, it's going to be interrupted to do reads. So there is, and then you have the redo log, so that's another source, and then you have the bin replication log. So you have n plus 2 write streams and many read read requests interleaving. There is this multi-stream proposal. There was a nice paper from Samsung. And the idea is that you could tag write requests or files based on their predicted lifetime. For leveled compaction, files at the top of the tree have a short lifetime. Files at the bottom of the tree have a long lifetime. If you then, so what you're doing is telling the storage device, keep short-lived files in one erase block on the SSD and keep long-lived files in other erase blocks. So files would be more likely to die together, so that the worst case is to mix everything completely. If you want to minimize the amount of copy out you have to do in Flash, the firmware, when it's copying, it picks an erase block to clean, so it can be rewritten. It has to copy all the live data out of that erase block and copy it elsewhere. You want to minimize the amount of copying out it has to do, because that's an additional source of write amplification. So if you can co-locate short-lived files separate from long-lived files, you achieve that property. The problem now is the SSD vendors are debating over how to put this into the standards. So we know a way to do it that works great for LSM. The vendors don't just want a solution that works great for RocksDB, because the world is not only running RocksDB on persistent storage. So I understand the delay. I'm just hoping it gets through. To co-locate, there's always concurrency. I just want to co-locate short and long-lived writes separate from each other.
Okay, let's thank the speaker again.